welcome to the class of intelligent product design. So, today we will talk about something which is beyond what we have just talked in the last lecture, which was all about the structures. So, we had the concept of a particular design with us, and then the materials we have procured, and we have thought of a structure for static or dynamic purpose. But then many a times we have to have some specific functions, and these specific functions may be in terms of some positional change, maybe in terms of generating some velocity or acceleration, or maybe force. Now, in order to do all these things, we need to have two kind of possibilities with us. One possibility, which we will discuss in next 1 and 2 lectures, is related to something which is called physical intelligence, and this possibility is with the help of some mechanisms which will be predominantly passive, but also it can be active. If we need, we can also make it active with the help of certain powered sources, energy sources like motors, etc., actuators. Now, the role of such mechanisms will be basically to transform the motion, let us say from position to force, and so on and so forth. Now, in that direction, I will first talk about different mechanisms that we can adopt for intelligent design. And you have to also keep in mind that the application of mechanism is not something new. For thousands of years, like starting from the potter wheel, then the development of clocks of various form, think of the mechanical watch, a fully mechanical watch, such a complicated mechanism it has evolved. All these are the stories of how to transmit the motion and transform the motion, even including the cryogenic rocket engine that is used today for the taking the satellites to the long distance orbit like geostationary orbits. The mechanisms are spreaded everywhere, and the mechanisms are the first gateway for intelligent design, because mostly you can design a system intelligently, something that we will call as the physical intelligence. Physical intelligence, if we know that what will be the corresponding motion transmission and transformation systems. So, let us start to see these different types of mechanisms. Now, in order to look into these mechanisms from a slightly informed point of view, we must have the concept of what we call the degree of freedom. Degree of freedom, once again, is related to something which is called kinematics. Now, there are two terms that are very much important for a dynamic system. One is called kinematics, another is called kinetics. Kinematics is where we are only bothered about the motion transfer, and kinetics is where the force, the energy that is required corresponding to this transfer of motion is also included in the system. So, if we first consider kinematics, the motion transfer from one body to the other, then the degree of freedom refers to the minimum number of independent variables required to define the relative motion of two rigid bodies, which are in terms of a relative motion with respect to each other. Now, when we consider one single body, let us say this particular system in the space. So, how many degrees of freedom it can have? Well, it can have the motion in the z direction, the motion in the x direction, and the motion in the y direction, whatever way you define x, y, z, but 3 translations it can have. Also, if I consider certain axis like this as one axis, then it can have this kind of a rolling motion. So, this is a rolling that is happening. It can have a motion which is like pitching up and down, and it can have a motion which is yawing. So, it can have 3 rotation and 3 translation, total 6 degrees of freedom. However, the moment I join it with another object and these two objects have certain constraints, then all these 6 degrees of freedom may not happen together. Okay. So, just for example, if I just fix it with respect to my fingers, then it may restrict its movement certainly in the direction of towards this. So, if I refer it as say the z direction, maybe it will not allow. If I keep it fixed, maybe it will not allow x direction also, and maybe it will allow only a rotation. So, like that, the moment you have 2 rigid bodies joined together, this individual 6 degrees of freedom may get lost, and it will come down depending on the degree of constraints that it is going to apply. So, for a kinematic pair, we have to now know that how many degrees of freedom we are going to allow for a system. Now, different mechanisms or joints, so to say, would offer different types of degrees of freedom. For example, if I just look into the slider crank mechanism, we can see that it is only allowing 1 degree of freedom, okay? And the motion is transformed from the rotational motion here to the sliding motion in the slider crank mechanism. If I consider a cylindrical joint where these 2 rigid bodies are attached together, so what kind of motion it is going to allow? Well, we can see that it is allowing 1 rotation as well as 1 translatory motion. Spherical joint, on the other hand, is going to have 3 degrees of freedom. So, you can see here that you can actually have here 3 degrees of freedom in terms of pitch, roll and yaw. That means, you can have a yaw motion, you can have a pitching motion, okay, and you can have a rolling motion in the system. So, thus you will have 3 degrees of freedom in a spherical joint. Let us look into the kinematic pairs very closely. As I told you that a kinematic pair is a connection between 2 physical objects that constrains their relative motion. The nature of the connectivity will define that what kind of constraints are there. And we have to also keep in mind that these kinematic pairs are the basic building blocks of any mechanism. So, they determine the type of movement or behavior or response of the system that would come up. Now, if the kinematic pairs have a lower pair, that means that the 2 rigid bodies are going to be surface wise in contact with each other. So, their surfaces are going to touch against each other. You can think of, for example, this revolute joint, the entire surface is in touch with the other body. So, this is body 1 and body 2, the entire surface is in touch with. Something similar like this is body 1 and body 2 is going to happen for the prismatic joint also, that the entire surface will be in touch with the between 1 and 2. Okay. So, these are the definitions of lower pair. There are 6 different types of lower pairs. The revolute joint is one, the prismatic is the other, screw is the other, and then the cylindrical, spherical and planar. Also, if you look at it, that the revolute joint is going to give you only 1 degree of freedom, prismatic joint is also going to give you 1 degree of freedom. Screw joint is something interesting, that even though there will be a rotation and a translation, but they are related to each other. So, hence you are going to get only 1 degree of freedom. Cylindricals are going to give you can see 2 degrees of freedom, planars 3 degrees of freedom. Spherical also you are going to get depending on the situations 2 to 3 degrees of freedom. That is, you can have 3 rotations, all of them together, and in some cases 1 rotation may be constant. So, these are all the definitions of lower pairs. Then you have higher pairs. Higher pairs, the simplest example I always say is that you take a semi cylinder, cut a cylinder into half and then put it in a flat plane. Okay. So, that you can now see that it can have 2 motions like this particular, you see it is only this line which is in touch with this plane, and it is going to have one motion this way, one direction, and also it is going to rotate. So, you can have 2 degrees of freedom in this higher pair, but higher pair's definition is that the 2 members will be either touched in a point or in a line. Okay. So, like the gears, best example, or the cams, belt, ropes and chain drives. Now, then there is also the third type which is called wrapping pair, because you must have also noted mechanisms like, let us say, pulley based systems, right. So, these are examples of wrapping pair. So, when one member completely wraps the other, like belt and pulley system or chain and sprocket system. So, these are all different types of kinematic pairs. There is also another way we can define a kind of the mechanisms. This is in terms of the form closed and the force closed pairs. Now, form closed, what does it mean? It means that geometrically the 2 bodies can have the relative motion against each other without the application of any external force. So, that is the form closed pair. For example, a cylindrical pair is a form closed pair, and force closed pair is such a system where this is to be maintained with the help of an external force, for example, a cam follower. So, this is another way of defining a particular type of a moving system or a mechanism. Well, when we talk about the constraints, then there are 3 types of constraints. One is called a completely constrained motion. So, it is defined as the type of motion where the motion of pair is limited to only one direction, like this is an example. Motion is only limited to this direction, you cannot rotate it also. And then incompletely constrained motion, where the motion can be this way as well as there is nothing constraining the 2. And then partially or successfully constrained. So, even though this system has the potential, but let us say if I put a collar like this, it will happen that it will not be able to basically move, but it will be only able to rotate. Or if you put a system of gears, a system of bearings here, that can also serve the similar purpose. So, these are called partially or successfully constrained motion. So, you can see a completely constrained motion, you can see a incompletely constrained motion where it can move as well as it can rotate, and here you can see only rotation, the movement is completely constrained. Now, we know about these kinematic pairs. Now, let us talk about kinematic chain. Kinematic chain is a mechanical system which is made up of rigid bodies or links that are connected by joints to provide constrained motion. So, here you need not have only a pair, but maybe n number of such links or rigid bodies joined with each other. One of the very popular such mechanism is called a slider crank, which I have earlier also shown to you. The other example which is also very popular is called the 4-bar mechanism. Okay. The reason we call it 4-bar is because we consider this base to be another link. So, 1, 2, 3 and 4. Okay. So, that is the 4-bar mechanisms. However, there can be a link based system which does not allow any motion at all, like if you consider this system. So, this is not a kinematic chain, even though there are multiple links together. So, this system does not allow any motion to be happening into this system. So, it depends on the type of joints, how it is connected, and the degree of constraints that is there, from which you can make out that whether you are going to get a mechanism or not. Well, so one of the most popular mechanism I told you is a slider crank mechanism. So, if you look at it very carefully, that what is slider and what is crank? Crank is basically this part which is rotated, which is the input part, where you are actually giving energy to this link for the rotation. Then you have a slider at the end, and the two crank and the slider are connected. So, it is called a connecting rod. Okay. And you can fix a frame and see how it is happening. Now, even though this is in principle the description of the complete system, but I can actually stop the motion of each part of this system, like the crank arm or the connecting rod or the slider, and I can get different types of motions out of this system itself. So, this we will call that, even though it is based on the slider crank, but if we take away some more relative motions, we will generate what we call mechanism inversion. Okay, let us say what are the mechanism inversion that we can actually have. Well, one example is, if you look at the internal combustion engine, the piston inside the cylinder of a car engine, it will only move back and forth like a oscillatory motion. So, how it is happening, that that this is the way it is going to happen. So, this is a standard slider crank mechanism inversion 1, and then inversion 2 is that where the crank is fixed. So, here I am fixing the crank part, and the slider reciprocates due to the rotation of the connecting rod only. So, this is rotating. So, whereas this part is fixed. Okay. So, like the rotary engine or oscillating cylinders, particularly you would see these example, very interesting example. For each one of them, you would see in the reference we have given, that where you can find it out. So, the Siemens Halske as example, where you would see that this kind of a oscillating cylinder is developed using the inversion of the mechanism. So, you can see it here, that the crank is fixed and it is the connecting rod that is with the slider is creating this motion of the system, and that is something where a multiple piston cylinder is actually getting energized by the mechanism. So, this is inversion 2. Inversion 3 can be that the connecting rod is fixed, okay, but the crank is working and the slider is working. So, that will create an oscillatory motion, which is known as a very famous one. It is called Whitworth quick return mechanism. So, you can see this is something that is used for shaping machines, or so to say, to give a finish to a system, slotters, planers, etc. And you can see here that the connecting rod is fixed all along. Okay. So, it is the slider and the crank, okay, that is creating this relative motion, and that is what is creating this kind of a oscillatory motion. All shaper machines are based on this principle. Now, the inversion 4 is that the slider is fixed and the crank rotates continuously, and the oscillation is happening in the connecting rod itself. So, typically pendulum pump, bull engine, hand pumps for water, they all follow this type of a system. So, you can see that how this system is going to work. So, you can see here that the slider is fixed. So, the crank is rotating and this connecting rod is actually oscillating in this system. So, you can look at it very well, that this is going to happen to the system. So, the slider is fixed and the crank is rotating, and the connecting rod is oscillating. So, this is one such system. Now, we come to another very popular mechanism, which is called the 4-bar mechanism system. Okay. So, in a 4-bar, as I told you that this is the frame, this is the driver or the input. So, this is where we give the input motion to the system, and then there is a coupler and then there is a follower. So, if this input motion happens, number 4 also starts to show a motion. Okay, so, that is the basics of a 4-bar mechanism. So, we have the frame part of it, then the crank or the driver, that is the input link that rotates continuously, then there is a coupler, and then there is a follower which follows this motion of the system. Again, in this case also you can have various inversion. First inversion is that it is frame fixed or crank rocker mechanism. So, the frame is fixed and the crank rotates while another link oscillates. That is a very standard, okay, and that is something that you would see in oil, for example, exploration. You will see continuously this mechanism will be working. Okay. So, this is the crank rocker mechanism. There is a particular condition of course there, that is this S and L, the length of them together has to be less than P plus Q for continuous movement. This is something that you have to satisfy. So, this is something that we will see in the pump jack mechanism in oil wells. The crank is the input and the follower performs the oscillatory motion. Now, another inversion that is possible is that the crank is fixed or there is a double crank mechanism. So, the crank is fixed, the coupler and frame make complete circle and rotates the continuous motion. So, if we look at the system and there is a condition of course that you have to satisfy here, and if you now look at the system, you can see that the crank is fixed and it is the coupler and the frame that is creating this complete circular motion of the system. So, that is the inversion 2 that is possible from such a system. Now, I go to inversion 3. Inversion 3 is called parallelogram mechanism, something that is used in pantographs for example, or also for the copying and scaling. Okay. Today, we may not be using this, but for engineering drawing, the use of drafter is something which is having the similar mechanism, that is the parallelogram mechanism system. So, here the condition is to be that the opposite links are to be of equal length. So, that S and P are to be of equal length and L and Q are to be of equal length, and S plus L has to be equal to P plus Q. Now, this, as I told you, that this is used for copying or for pantograph type of applications. Okay. So, you can also see it how it works. Okay. So, must have seen it that the railway pantograph, the way it works is exactly similar to this kind of a inversion 3 of 4-bar mechanism. We then come to inversion 4 of 4-bar mechanism, which is also known as a double rocker mechanism. So, in this case, what is going to happen is that the two links will oscillate, okay, but they will, none of them will have a complete rotation that we have seen so far. So, there will be only a kind of a particular range of oscillation of the driver link as well as the follower link. Okay. The condition of a double rocker is that S plus L has to be greater than P plus Q. So, you will not get any full rotation in such a system. So, you can see that how such a system can work. So, you can see that essentially both these links are having an oscillatory motion. Okay. So, that is inversion 4 of the system. Using these kinds of mechanisms, not just one or maybe many of them together, you can create many interesting products. Table is one such system where you would see the application of such mechanisms. So, let us just see one by one such tables. Okay. In table 1, you will see that the linear motion is actually converted to rotational motion. So, this is a table 1. You can see that it is having the inversion, and in the case of table 2, you would see that it is converted to the rotational motion. Okay. The rotational motion is converted to translatory, the linear motion. So, basically in both these cases you have two slider crank mechanisms together. So, whatever we have seen, the slider cranks, the 4 bars, you can actually take a number of them together and create many complicated systems. Table 3, if you look at it, it is even more fascinating. Table 3 is the so called Fletcher capstan table mechanism, and you can see that it has 13 leaves, and it can be expanded by rotating, the entire table can be expanded by rotating 120 degree. So, that you can get two different sizes from the same table. So, these are different types of applications of mechanisms. Okay. By adding all of these types of these mechanisms together or compound mechanisms together, you can get such a system. So, this is about the basic mechanisms. Now, I will show you very quickly some more complicated one, like a 5-link mechanism of door 1. Look at it, that how this is working. So, fixed wall is 1 link, and then it has 4 linked system, and this is one mechanism. See the other type of a door opening, this is door 2. It is a modification of slider crank mechanism, where the center of the rotating link is actually translating. So, this is door 2, and then you see door 3. This mechanism is also a modification of slider crank mechanism, and when a load is applied on a link, it moves downward. So, this downward linear motion is converted to the rotational motion of the gate. Now, let us see some other mechanisms. So, let us see some mechanisms further, like the agricultural products. Okay. Say the planting is mechanized in the form of machine. So, you can see that how this is happening. These are actually more complex mechanisms, where a combination of 2 or more mechanisms are used to obtain the desired motion. Like this planting mechanism has 3 mechanisms in it, 1 slider crank and 2 parallelogram mechanisms. And you look at the harvesting mechanism, also another example of a complex system. Again, you look at the other one, that is the weeding robot, and you can see here that each weeder end effector is essentially a 3-DOP system. The constrained motion is achieved by 3 motors controlling each degrees of freedom of the system. So, these are some of the mechanisms that are based on whatever simple mechanisms we have talked about, but many of them together creating a more complex one. I will show you another series of it, the wiper mechanisms. So, wiper is one field where lot of physically intelligent system, as well as we later on see embedded intelligence systems has gone for developing such systems. So, wiper mechanism is one. Then you look at the beautiful Tesla butterfly door mechanism. So, this is again another fantastic example of how a simple mechanism based system without any closed loop feedback, etc., you can get a very complex motion out of it. And also see the convertible car roof mechanism. So, these are convertibles. Okay. So, these are all different types of complex mechanisms that you can generate starting from these simple mechanisms. Okay. So, this is what we have seen in terms of cars. Now, for the aircraft also, the landing gear mechanism, if you look at it. So, this is a modified slider crank mechanism, and then if you look at the wing flapping mechanism, again the slider crank mechanism is used here to push the flap outward, and then other links are used to constrain the outward motion. So, it is a complex system. And also another interesting system I want to show you, much different from the other doors that we have seen, but this is a aircraft door mechanism. So, you can see that it is a 4 bar, essentially a 4 bar mechanism, but it is quite complicated in terms of its application. Thank you.